So I'm interested broadly in the relationship between social networks and health, which is not really new, and a lot of people study this, but I like to think that I try to study it in a way that's a little bit different or goes a little bit beyond the literature in general in two ways. And one of those is that I like to study not just networks as a predictor of health outcomes, but also how social networks are dynamic and responsive to health crises in people's lives. So that's a way that's much more understudied than the opposite direction. And then in addition, I really try to dig in to understand what are the mechanisms, both behavioral and biological, that underlie this relationship between social networks and health. So how do social networks influence health outcomes and those pathways, and then how do they moderate them as well? So my research examines things like decision making, like how people decide whether or not to use preventative health care, for example, as a result of their position in their personal social network. What kinds of access to resources they have, what behaviors they choose to engage in, how social networks affect things like recovery, not just whether you get an illness, but how the illness trajectory either goes poorly or goes well after you've been diagnosed. And then a lot of my research looks at phenotypic expression of genes as a result of moderating social network influences. And I decided not to talk a lot about that because that's what I talked about for my job talk, and so probably some of the people already had to sit through that once. So I'll just sort of briefly talk about my approach because this is a project that's ongoing. But I'm very interested in candidate genes and genetic risk scores that are associated with disinhibition or impulsivity. And so then those things increase the likelihood of substance misuse, abuse, and dependence because you don't have the sort of biological inhibition to not drink when drinking is really fun and makes you feel better when things are going wrong in your life. So I study social networks as a moderator of this process. And so I find that things like low social regulation, right? So you don't have people in your life that are sort of controlling your behaviors. Permissive social norms and access to drugs and alcohol sort of exacerbate the genetic risk for substance abuse and dependence. Conversely, if you are genetically at risk, but you have these sort of optimal social networks, then you essentially have no phenotypic risk despite having genetic risk for these outcomes. So that's sort of other things that I do. Today I want to talk a little bit about a new project, and it's very much in its preliminary stages, and we just applied for an R01. And the reason that I want to talk about this is because part of the reason that I was brought in for this position is to bridge to the medical school. And so this is a new project that I have going on with people that are in actually pharmaceutical sciences, pharmacy practice, and then also in the Link Center at the University of Kentucky, which is Steve Borgatti's shop. And in this project, we're interested in figuring out better ways to identify and measure a drug-seeking behavior called doctor shopping. And it's really interesting, and I didn't know much about this because, like most network science people, I don't really care about the application. I mostly care about the method and the theory. So this was really interesting to me when I was told about this phenomenon. So first, there apparently has been a prescription drug abuse epidemic in the United States. And I didn't really know a lot about this because I don't myself abuse prescription drugs. But apparently there's been this huge increase in opioid abuse, about 4,680% between 1996 and 2011. And so now the prevalence of prescription drug abuse exceeds that for all other types of illicit drug use combined, except for marijuana. And so we now know that mortality from drug overdose is among the leading causes of preventable death in the United States, and it's actually higher than fatalities from car accidents, which surprised me. So this is a really big problem, and lots of people are sort of trying to put their brains together to figure out how we can stop this tide, turn this tide. So doctor shopping is a drug-seeking behavior that ends up being really important in sort of the social landscape of prescription drug abuse. And so what this is obtaining controlled substances from multiple prescribers simultaneously in a given period of time. And so typically you're exceeding the recommended dosage for that drug. So for example, I might go to the pain clinic and say that my back is hurting, and so I get prescription drugs from that person, and then I'll go to my general practitioner and say that something else is hurting or maybe the same thing. And so basically through some sort of dishonesty, right, you're obtaining more drugs than you should have in a given period of time. And then I can take those and abuse them myself, or I can divert them, or in other words, sell them. So it's estimated that about 12% of all prescriptions written for any controlled substances are procured through doctor shopping. So this ends up being a pretty big chunk of the problem, right, of opioid procurement. And so nearly 40% of people with prescription drug dependence obtain their drugs, at least in part through doctor shopping, right? So you can imagine how they might combine this with other means of getting drugs. And so one thing that makes doctor shopping really important, and particularly the identification of doctor shopping, is that it's a really strong indicator of escalating abuse. So people tend to do this when they're desperate, right? And they're highly dependent on drugs. And so it's associated with a twofold risk for fatal overdose. So it's really important to identify this behavior and identify it early. But it's very difficult to identify because the measurement is really poor. So typically the way that it's measured is through something called multiple provider episodes. And so this is just a binary indicator, which right away we know is probably not going to be the most effective way to measure something. And so typically what this means is it will be that they saw 4 or more providers, for example, in a given period of time, and they got prescription drugs from those different providers. And so this creates a lot of type 1 and type 2 errors, right? Because people who are sort of early in their drug abuse trajectory, or people who just constantly keep themselves on drugs but they're not exceeding the recommended dosage, those people tend to fly under the radar. So what you're picking up here with these measures are people who are very severe, right? Very severe doctor shoppers. And then in addition, it also creates the opposite problem where you have people who have chronic diseases or late-stage cancer. And so these people actually tend to see lots of different providers and need a lot of pain management, and so they get picked up. So really this is a big problem, right? And so it's a problem for things like prescription drug monitoring programs, right? Because we want to be able to very accurately identify who's engaging in this behavior. So from sort of a policy standpoint, it's important, but it's also important from a research standpoint because it creates a lot of variation in estimates of how prevalent this behavior is. So estimates range from about 0.2% of the population to 8% of the population has engaged in doctor shopping. And so when you have this big of a range, it makes it difficult to really understand the etiology of doctor shopping. And so it makes it hard to evaluate things like prescription drug policies, right, which are implemented to try to reduce the impact of this problem on population health. So in terms of the characteristics that are involved, we know that doctor shopping tends to be used by a subgroup of people that are averse to illegal behavior, right? So it tends to be women are more likely to doctor shop, patients who are older, those who are higher in socioeconomic status, and people who take their drugs orally rather than injecting them. And so these are people who, in a typical clinical encounter, would not be likely to raise red flags for providers. So for this reason, they're not checking the prescription drug monitoring information, and so this makes these people a lot harder to identify. So in addition, there has been some research using very small convenience samples recently, which suggests that characteristics of physicians end up being really important too in determining these patterns of doctor shopping. And so physicians may be systematically targeted on the basis of their prescribing behavior, or on the basis of other characteristics, right? So there's some indication that things like being in a solo practice may make a physician more likely to be targeted for this behavior. So this suggests that there's likely to be some sort of clustering, right? So in other words, particular kinds of physicians are more likely to be targeted by particular kinds of patients. In addition, there's some really interesting ethnographic research which suggests that knowledge of providers that are good targets or easy targets is shared amongst doctor shoppers. And so when I heard about this problem, I thought that this is a social issue that is ripe for social network analysis. So social network analysis is ideal for this kind of problem because the key mechanisms are relational processes, right? They involve seeking out someone to get something from them, so there's an exchange going on there. And there's also a flow of resources or information between patients and potentially providers that could end up being very important. And so also, I heard about this sort of problem right around the time that I was reading about some really interesting uses of SNA to identify structural anomalies or fraud in industry and financial markets. But this has never been applied to this issue of prescription drug abuse. So I decided to get my hands on some data, so I hooked up with these people in pharmacy. And when I saw the structure of their data, it became clear that I would need to use a two-mode social network approach, right? So we have your typical one-mode network here, where you've got ties between people in one class or category of actors. And then your two-mode or affiliation network is when you have ties between actors that are in different categories, but not ties between people in the same category. So if we're thinking about this doctor shopping, you're going to have prescription ties between doctors and patients, but not between patients and not between doctors. And so what you can then do is convert this into a weighted one-mode affiliation network, which is what we did. And so now you have essentially co-prescription ties between two doctors, and those are weighted by the number of common patients that they have, or the number of patients that they both prescribed these controlled substances to. And so with this two-mode SNA, we can look at prescribers that are linked indirectly through co-visitation by the same doctor shoppers. And we can look at patients who are connected through visiting the same physician. And so we can look for clustering. I wasn't really sure what we would find here. I wasn't sure if we would find a lot of clustering or not. Maybe it's really pretty random which people, individuals go to for doctor shopping. And so then the sort of ultimate goal is to develop social network measures of doctor shopping that are more sensitive than the multiple provider episode measures that have been used before. And so then once we develop these measures of doctor shopping, we can identify characteristics of central actors. And hopefully that would allow us to better identify this behavior early on and implement some sort of interventions for stopping it. So the data that we used are de-identified patient health claims information from a large commercially insured population from 2007 to 2009. And this is 15 million patients annually, which can pose a bit of a challenge for social network analysis, which is why we have people like Kadi who solve these problems for us. So that's what I did. I went and got somebody to help me out. And so these are people both that have private insurance and people that have Medicaid. So that's important, right? We don't just want a bunch of rich people in our analysis of doctor shopping. And it was important to use a very large data set because if we're trying to translate this information to practice, there are going to be these large state databases or federal databases, and that's the kind of big data that this would be used on. So it was important to be able to determine feasibility in that same sort of data context. And so these are nationally representative of the US with regard to gender, regional distribution, and age. So the analysis sample is going to be any patient who filled one or more, here we used opioid and benzodiazepine prescriptions because those are the two commonly abused controlled substances, and every clinician who prescribed to one of these patients. And so what we end up with is about 5 million patients and about 700,000 prescribers that prescribed any controlled substances or accepted prescriptions for any controlled substances. And so what we wanted to do for the grant application was a preliminary analysis where we use a priori identification of doctor shopping. The ultimate goal is to use these SNA measures deductively, right, and to find sort of more more nuanced measures that aren't binary. But for this, we just wanted to identify whether there was clustering and how much clustering there was. So we identified doctor shoppers using what's called a 4+4 criterion. And so this is 4 prescriptions plus 4 pharmacies. And so the number of pharmacies becomes important because if I get all of my drugs at CVS, then pretty soon CVS is going to know that something is going on, right? And so I need to go to CVS and Walgreens because those are often not connected to each other. Okay. And so then I used the one-mode weighted affiliation networks of clinicians for this analysis. So that was the square all the way to the right that you guys saw. And so I'm looking at degree centrality, which is just a very simple measure of activity within the network, and this is number of ties to other clinicians through a common doctor shopper. And then I just did some basic correlations of centrality to other measures so that we could see if there was any sort of validity here, right? And then created a visualization as well, which is the most exciting part, obviously. So what we found is that there were about 89,000 clinicians who prescribed to at least one doctor shopper. And so that's about 12% of the clinicians who prescribed any controlled substances, right? And so what we found is that among these clinicians that prescribed to doctor shoppers, the mean degree centrality was 23. So they were linked indirectly to 23 other physicians through common patients, which is really high, we thought. And so then it turns out, if you look at the standard deviation, which is about 61, it's very skewed. So we have some people, very high degree of clustering. We have some people who are extremely active in this doctor shopping network, and then a lot of people who are much less active. And so you can see this in the range of degree centrality from 0 to 995, which means that we have one prescriber in the network who had been doctor shopped by 995 patients who also shopped another clinician. And that's in a 1-year period, which is really kind of astounding. And so here's a picture of the network. So the overall result is a very large network of about 7,000 doctors who are tied by 45,000 co-prescribing relationships. And so about 76% of those prescribers are connected in one main component. And so this is a picture of that component. And that component contains 99.96% of all ties. So most of the co-prescribing ties are represented in this network. And it's so big and so clustered that it's almost kind of hard to see the ties that are there. But I'm going to zoom in a minute. But just to tell you a little bit about this figure, the node size is your weighted degree centrality. So the larger the node, the more connections they have to other physicians through common doctor shoppers. And node color is community, right, which is an algorithm which tells you that people in that community have more ties to each other than to people outside. And then the line thickness is the number of co-prescription ties. So that's the weighted part, right? So in other words, if Michael is prescribing to 10 of my patients, then our tie would be weighted by 10. So that's the thickness of the line. And so what you see, it's very clear, there's a very strong core of doctors and then several important subgroups that emerge. So this is just a blown up version of that main cluster in the center. And so you can see it's made up of 4 different communities. And it forms a K-core of 19, which is pretty big. So this means that everyone in this K-core is connected to at least 19 other prescribers. And it's made up of 755 nodes, which is 10% of the overall nodes in the network, but that accounts for almost 50% of ties in the network. So very, very strong clustering in this network, much stronger than we anticipated. And you can see that there's substantial co-prescribing in this figure between some communities, but not others, right? So there's strong ties between these communities and that one. And so it's interesting, we've done a little bit of looking at what these communities are and where they're located. And so a lot of these are located across state lines, which ends up being really important from an intervention perspective because a lot of these prescription drug monitoring programs are within states. So if they're going across state lines, then they're not going to be identified. But again, with SNA, we can do everything. So we can get around that problem. And so this is just a figure of the ties between the communities of clinicians. And again, as we were saying, there's really strong connections between communities that are in different states. And so this might indicate that there's drug rings, or these might be pain centers, which tend to have like high activity in terms of prescribing to people who are drug dependent. We're not really sure yet, but that's what's exciting about this, is we get to do all those kinds of analyses. So then we just did some simple correlations of clinician degree centrality and aggregate patient characteristics. And so what we find is that people who are more central in this co-prescribing network have patients who, on average, are more severe in terms of their degree of doctor shopping. So those patients, on average, of physicians that are higher in degree centrality visit more pharmacies on average, more different pharmacies. They have a larger number of prescriptions on average, more multiple provider episodes, which means more sort of overlap in the amount of drugs that they're being provided, and then the average number of repeat visits. So they tend to go see the same physicians if those physicians are more central in the network. With regard to sociodemographics, this is not what we expected from previous research, which is either terrifying or exciting, depending on whether you're an optimist or a pessimist. But I'm kind of excited about it, because what it suggests to me is that if we use SNA, we might be able to uncover some patterns that were not apparent before. So there's no effect of gender, but we see that patients tend to be lower socioeconomic status when we're correlating with physician centrality, and also younger. So they're prescribing to different kinds of patients. And then probably the most interesting finding to emerge from these preliminary analyses is the impact of centrality on the quantity that's prescribed. And so I expected there to be more quantities of drugs prescribed by physicians who are more central in the co-prescribing network or more active in the network. But in fact, what you find is that they prescribe fewer refills, they prescribe fewer average days of medication, and also smaller dosages in milligrams. And so I'll talk about that in a minute. But so sort of to sum it up, we see substantial non-random clustering, lots of non-random clustering, which is really interesting and makes me very excited about this R01, and I hope we get it. But we see several very active communities, which could be, again, these drug rings or pain clinics, and they have ties to each other and ties to outside communities. And so this suggests that clinicians are targeted in a non-random way. And it also, we think, suggests collusion on the part of patients, right? So they're sharing information about who are sort of effective targets for this kind of behavior. And so clinicians who are active in the networks have significantly different patient populations. So they're involved in more serious drug abuse or diversion, which suggests that whatever kind of collusion is going on is effective, right? And so they tend to be lower SCS and younger. But again, in terms of the most interesting finding about patients is that clinicians who are more active in the co-prescribing network tend to prescribe lower quantities per patient. And so, of course, my naive sort of interpretation of this was, well, maybe they're a little bit suspicious, so they want to, err on the side of prescribing lower quantities. And then my friend, who's also on the project, who's a criminologist, was like, oh no. They want to, basically, she thinks that these people are complicit and that they prescribe lower amounts so that they can ensure that there's going to be continuing demand for the product, which is, yeah. So I don't know, who knows? I mean, we'll be able to hopefully figure this out from some additional analyses. So in terms of the unique insights of social network analysis, I'm hoping that we're going to be able to reduce errors of classification using SNA and get measures that are more nuanced and more sensitive than the ones that we currently use. And so what we find here, or what this suggests, is that who patients are targeting for doctor shopping may be just as important as how many doctors, right? So you may be seeking out prescriptions from fewer providers, but if those happen to be the providers that are the perfect targets, then that might say something about that person. And so hopefully we can identify those types of people better with these kinds of methods. And hopefully it will improve our ability to detect early signs of prescription drug abuse or behavior that is intermittent or less intense, but nonetheless problematic and potentially an indicator of worsening abuse. So in terms of future directions, we want to establish more deductive measures of doctor shopping, and then establish the validity through a variety of psychometrics, and then use these network-informed criteria to examine characteristics of doctor shopping patients and their clinicians. That's sort of where we're going with this project. So, and that's it. Thank you.
One thing I found interesting when you were talking about your finding was that religion did continue like lower SES, but then also in this sort of pattern of going across state lines. And you know, depending on which state, that can be very expensive. So I think that's interesting because the tension between those two points.
Yeah, that's true. That's really interesting. I mean, I think once we sort of dig down further into the data, we'll be able to hopefully identify what kinds of patients are using this more for diversion, right, or for illegal sale, and which ones are using it for personal use. And so I'm wondering if that finding wasn't driven in large part by these major doctor shoppers who are using it more for diversion. So if your livelihood is dependent on you getting those different drugs, I mean, you can sell an Oxycontin in Appalachia for like $20 to $50 a pill, depending on the strength. So it may well be worth it, right, economically, to go across state lines if you're using it for resale, right? So I think that's a really important distinction that we need to, look into. Yeah, absolutely. But that's, kudos for identifying that. Yeah. Yeah. Right. Well, low documented income, right? We do. Yeah, we do. And so that's another next step that I didn't mention. But so we have 3 years of data. And so our plan right now is to break them into 6-month increments, and then, be able to look at network change over time and what's driving network change. And that's probably another R01 after this one, because that's, even more complex. The first one is really the feasibility R01. So yeah, we do. And so you can think about all the amazing things that could be done with this. Yeah.
Well, so you've already mentioned you have a criminologist on your team.
Criminologist. Yeah. So we have a criminologist, a sociologist, that's me. We have an actual pharmacist, so she's a clinical pharmacist, and so she provides a lot of really important information about, the actual sort of interactions between physicians and pharmacists and patients. And then we have a professor of pharmaceutical practice and research, and so he studies prescription drug monitoring programs and sort of broader macro patterns in prescription drug abuse. And then we have a postdoc from the Link Center who works currently with Steve Borgatti, and he's a sociologist by training. And so, he works with me on ginormous data sets and analysis.
Even think about injecting into the prescriber network people which are actually knowing more about what's going on, detected, potentially helping them to understand, hey, it's going to be detected that I'm doing this. And then, of course, they will develop new strategies.
Yeah. Yeah.
But I think you can ultimately try to change doctors' behavior and that doctors basically do follow what other doctors are doing.
Exactly. Right, and so that's why the sort of the point of service has been identified as a really key sort of place to identify this sort of behavior, but it's the PDMPs and the strategies that are used currently don't work because something like a third of doctors don't even check PDMPs. They don't pay attention to what other doctors are doing. And if it's lower level, they might just sort of be like, well, whatever. And so what's happening is that people are circumventing this by going across state lines, by staying sort of just under the radar of what would be detected by a prescription drug monitoring program. And so the idea is if we develop these more nuanced measures, hopefully we could, change, provider behavior or pharmacist behavior in a way that would be more effective.
But the technical problem is another question.
Oh.
So if you have these electronic health records,
Mm-hmm.
there is nothing which couldn't that would prevent, maybe there are privacy issues that prevent, but you could just see, all right, this patient was often seen by those people who got this kind.
Do we have national health records in the United States?
No, not that are all linked together. So these are through, yeah, no, except the insurance records. So these are electronic health records from an insurance company. But the downside of the upside is that it's national. So you can see the across state line stuff. The downside is that it, doesn't get anybody who's not in this particular insurance network. Now this is one of the largest insurance companies in the US, and they do cover Medicaid patients as well. So it's better than some data sets in that regard. But yeah, it's right. It's not ideal. So ideally, what we'd like to show is that this is feasible to do on a very large level so that we could try to, push the government into having national electronic health records that they could use for this kind of analysis.
Also relevant for the pharmacy if they ever would know what things actually go to the
Absolutely. Yeah, for sure.
Very good. Thanks so much.
Thank you.
Thank you. Okay, thank you. And thanks to Caddy for having me here. I'm really happy to come and visit with you guys and learn about what you're doing. It's all really fascinating. I'm Michael McLennan. I'm from Purdue University. I'm the director of this HubZero project. And I wanted to tell you a little bit about HubZero and kind of how people are using it to connect to data and tools and to each other. So first of all, what is HubZero? It's an open source software platform that we put out. We developed at Purdue over the last decade or so, and people use it to create websites for science. So for research, for education, and for collaborating online. And some people call those kinds of sites collaboratories or science gateways. We just call them hubs because they kind of tend to be a focal point for a community to kind of work together online. So that's basically what it is. It's web software to build these kind of websites, kind of a word. I gave a talk once, somebody said it's like a WordPress blog on steroids or something, a lot of steroids. But the best way really for me to explain it is to show you kind of a video of what it is. So hopefully this will work okay on the monitors without making the video card crazy. All right. So this is the world of HubZero. Again, people all over the world are using these websites. So photorealistically generated users, just like this one, sitting in their living rooms, accessing all of these various sites depending on what they're interested in. So there's a site, for example, for nanotechnology, the original Nano Hub. There's one for earthquake mitigation, where they're shaking buildings and seeing how they fall apart. For pharmaceutical manufacturing, for molecular diagnostics, and so forth. So these are all the different hubs that people have built using that same HubZero software stack. They all work the same way, but they're all different communities. There are more than 60 of these now running all around the world, and if you put them all together, they serve more than 1.8 million people each year. So let me show you what these people are doing. We'll start with a group at Penn State. This is a group that wanted to be able to put up a tool for an online class. So they went to NanoHub and they started resources upload. And of course, if you're going to contribute something to a hub, you have to have an account and log in. You can sign in with Google or Facebook or register an account. So they logged in. If they click Get Started, then it asks them what they want to upload. Is it a seminar or a paper or, in this case, a tool? So they filled out the form for a tool. Just give it a short name, who's on the team, whether or not it's open source, and all of that. So filling out this form creates a project area and a Subversion source code repository that you can work in and work on your tool. It also gives you access to something that we have called a workspace, which is kind of a Linux desktop that runs in the cloud. And it has all of the software for the hub kind of pre-installed, and it gives you access to clusters and all of that. So you can get into a workspace and you can make your tool run and then deploy it. And you can put anything in here. You can use MATLAB, Java, Qt, whatever your favorite programming language is. If it runs under Linux, it's good. But a lot of people come to us and say, well, I've got this old Fortran program that's kind of written for the command line, or an old C program. And so this Rapture toolkit that you're seeing here is a really easy way to create a graphical user interface for those old programs. So you drag and drop a couple of number controls, and you say it produces a curve, and you annotate it with a label and description and units. Here I'm adding a note, a little bit of HTML documentation to the tool. And again, I can preview the tool and see now this is what my tool is going to look like. 2 numbers on the left produces a curve on the right. So I'm in pretty good shape of creating my tool here with drag and drop. I can also go in and say what language I'm targeting, in this case Python. And when I go ahead and save it now, it'll save 2 things. It'll save an XML description of the inputs and outputs for the tool, and it'll also create a skeleton program for my Python program. So I'm saving those 2 things, and if I go in now and edit my Python program, there's all the gobbledygook that Rapture adds automatically for the inputs and outputs that you defined. And then there's a comment that says, add your code here. So you just go in then, right there, and add your Python code for the simulator using the numbers on the input side, producing outputs on the output side. So here's the finished tool. You fill in a couple of number values, you click Simulate, it goes off and runs that Python program that we just looked at. So that's how it works. And then we have a framework for deploying that tool. So in this framework, kind of a content management system, you can click Launch Tool, and it'll pop up the tool and kind of preview it for you so you can see what it's going to look like when it's finally published. And then there's a link that says my tool is working properly. And you click that, and it gets published. So for this tool, there was a user in the UK that was actually fabricating nanospheres in the laboratory. And he went to NanoHub and was searching around for stuff, extinction efficiencies and scattering and so forth, and found a lot of stuff, seminars, questions, all kinds of things on the hub, but most importantly, that tool that the Penn State group put up. And you can see there's like 600 people using the tool. It's been used in class, a couple of citations, but you can just run the tool just by clicking Launch Tool. So this is what the guy in UK did. He clicked Launch Tool. This is a more complicated version of the simple thing that I was showing you I was building. But same idea, you fill in some values, you get a plot, you can change material types, simulate again. So here I've got 3 different kinds of materials for the nanospheres, and you can see their kind of optical properties. I can look at absorption or scattering, I can zoom in on the plots, I can mouse over values, find an interesting peak, what's the wavelength of that. And then I can also download all of that stuff to my desktop. So when I click download, it'll download all the data that I generated from those simulations, and I can save it, put it in my own spreadsheets, and plot it. And that's exactly what this guy did. In fact, he ended up writing a paper about this, about the results on NanoHub and his experimental results. So changing gears, here's another application. A researcher at Purdue who was doing an agriculture study. And she went to this Purdue University research repository. This is Purdue's institutional data management solution built on HubZero. So it's basically another hub that does data management. And she logged in. She created a project area for her project. So maize grain yields, again, agriculture application. And if you want to describe the project, you can add a little bit of an abstract. So if somebody sees the project, they'll know what the heck it is. Oh yeah, this is that one that Sylvie created for the maize grain yields. You can add an icon. If you have about 50 projects, it really helps to have icons so you can recognize at a glance which project is which. And there's some controls too. You can say whether or not the project is visible to anyone or whether you want to keep it completely hidden. So the only way you can get into it or know about it is if you're invited in. But at least if it's visible, then people can see the abstract. They still can't get into the data unless they're on the project team. Now that's what we're doing here. We're adding people onto the project team, inviting them in. And if you start typing someone's name, it brings it up, but you can also just put in their email address, and it'll send out an email invitation and invite them in to the hub. So all right, now I've got my team, a few people added in. I can always add more later. I click Save and Continue. One more thing that PER does in particular, it asks information about the project that the sponsored program office can use to make sure that people are actually following their data management plan. So this ties into our kind of university administration. So here's the final project now. It has a kind of a Facebook-style wall so that when you come into the project, you can put up messages and people on the project can kind of converse on the update wall. It also has a file repository that you're seeing here. This is kind of like Dropbox or you know, something like Google Docs or Google Drive. You can upload your stuff in it. Under the hood, it's a Git repository. So we're actually doing version document control, whether people know it or not. But there's a whole web interface that makes it super easy to upload your data. So here, I'm uploading a zip file. I can expand it, and it'll expand the zip, and it gives me all kinds of stuff that I can browse around. So anybody on the project now can get in here, get these documents, modify the documents, use them. There's also a connection on Google Drive, too, so you can connect it to your desktop. So we take a CSV file now, and we can convert it into a database. This took the CSV file and staged it as a MySQL database with a bunch of JavaScript controls. So we can preview the data, we can mark up the data, you can say what the columns are, description, data type, units of measure, and all that kind of thing. And that helps people clean up their spreadsheets and make them understandable. And then I can save this for now in the project area and share it with my project team because we've got a lot of work to do, cleaning up the data and making sure that it looks good. So I'll save this table inside the project, and now it's listed on the databases area. You can see there it is. You can see the CSV file. You can click Update Database if you want to reload the latest data from the CSV, or if anybody wants to access it, you just click that link, and it brings up, again, the latest version of that live interactive database. Now, eventually, we're going to publish that as a digital asset with a digital object identifier that anybody can access. But for now, we got a lot of work to do. So there's a to-do list capability where you can create these little to-do list items, and you can assign them to people on the team. You can give them a due date. You can have conversations about all of this. You can say, hey, I need to clean up the data. Where is the latest data? And I'll say, oh, look in this directory. That's, you know, we need to make sure that that data is incorporated. Double check these fields and so forth. So you can get into threaded conversations here, and eventually we'll check off that to-do list item, and we're ready to publish. And again, all this is being captured on the update wall. You can see all the activity. Even if I didn't put updates up, the system is putting updates up about who joined and all of that. Now, here's what a published database looks like. Here's a team that went down to Haiti after the earthquake in 2010, and they put their data on NICE-Hub at nice.org. And if you go there and search for Haiti earthquake, you can find a bunch of things, including this live database. It's got authors, you can see the project team, you can see a little bit about a description, but if you click Data View, it brings up that live interactive database. I can put in, show me everything greater than 6,000 square feet, and it'll winnow down the buildings to just the big ones, and then I can sort in order of severe concrete damage. And now I'm seeing the biggest buildings that had the most severe damage, and I can even put them on a map to kind of understand what happened in Haiti. So that's kind of a very quick fly-through of what HubZero is all about. It's lots of sites like that people are using to create tools and data sets and publish them and make them available for other people in the community to use. All right. Now, I want to focus in and tell you a little bit more. You guys like data, so I want to show you some of the data that we've collected on some of this. The biggest and the oldest hub is NanoHub. This whole project started with NanoHub back in 2002, and just for trying to help nanotechnology people share data and tools the way I showed you. NanoHub now gets 700,000 visitors every year. About 300,000 of them stick around and routinely use the site, so that's our core audience of 300,000 users. And there's lots of stuff, 360 simulation tools that people have uploaded and contributed, and 4,000 other resources. So a lot of stuff, a lot of activity on the hub. And social scientists have kind of found that interesting. They look at NanoHub as a source of information. It's not as big as Twitter or Facebook, but it's big for science. And there are different things that people have studied. One is, how are people discussing or using NanoHub in academic literature? So I'll show you a little bit of that. Also, what's the impact of NanoHub on education and tools in the classroom? And I'll show you a little bit of that. And then finally, think of NanoHub as a place where you do team science. So we can show you a little bit of that too. So starting with the academic literature, They have a team on NanoHub that's gone out and scrubbed Google Scholar and found more than 1,100 citations that people have been able to find in the academic literature. And this is kind of the co-authorship citation network. Each of the dots is a paper, and then there's lines between dots as co-authors, right? And they've looked a lot at those papers to figure out what they're about. You can see 80% of them are really research papers. There are some that talk about NanoHub as a cyber infrastructure and some that talk about its use in education. But the vast majority, 80%, are all about research. And in fact, you'll see things like this. You'll see a group that, for example, measured electrical characteristics of thin films and used a tool on NanoHub to calibrate their measurements. Or another group that just used a tool on NanoHub to hypothetically figure out how the next generation of integrated circuits is going to scale going forward. So these are the kinds of things that people are doing, kind of the impact on the academic literature. And there's a lot more drill down, I suppose, that happens in that analysis, but that just gives you a quick overview. Now, I also mentioned education. People put up tools, people use them in classrooms. So for example, instead of copying out of a textbook the night before a lecture, a professor will come into class and just bring up a tool. And a student will have a question and they'll just pull up a material type and they'll say, let's see how it works, right? So you can use them in classroom. You can also assign it to students. Let them do the work. Let them optimize a particular electronic device or figure out what material works best. So hands-on or senior design projects kinds of things. And so far, we found about 22,000 students that have used NanoHub like this in class at about 185 institutions so far. And again, it's interesting to see how we figured that out because surveys aren't really going to cut it. So I have this little video that kind of shows you some of the data. So this is kind of a history of what people are doing on NanoHub. Each line in this video is a person. So if we look up at one of these lines, think of that as a person. The green dot represents a particular tool. The orange dot represents another tool. And you can see their pattern of activity over time. There's a time when they joined the site and then what they did with various tools. And if you look at all the different users on the site, kind of like this, just dumbly, you can see these correlated patterns of activity. This yellow block here, the green stripe, the purple stripe. Those are classes. There's a homework assignment that's due on Friday, and everybody is using the same tool for that. And a different homework assignment the following week, and so forth. And if you just look at this data, it just jumps right out at you that people are using this in coordinated ways. And it turns out we came up with a clustering algorithm and did some more processing and then followed up with people. And sure enough, yeah, they said, yeah, I was part of a chemistry class at Northwestern or whatever. So using this kind of analytics, that's how we've gotten to the numbers. We could figure out, because most people don't tell you they're using it in class. Most professors won't tell you that they're planning to use it or whatever. But by looking at the coordinated patterns, we've been able to kind of figure it out and quantify it. All right, now the really interesting thing, I think, is when we take those two things and put them together. So I imagine if I could figure out for each tool how much it's used in education, and I put that on one axis. And imagine for each tool, I figure out how much it's being used in research, and I put that on another axis. Then I might have a tool, for example, that's being used a lot in education and a little bit in research, or another tool that's being used a little bit in education and a lot in research. And you can kind of see where tools sit in that space. And you can, more importantly, follow them over time. So let me show you that. All right, so here is a plot of tools. You can see when a tool is first invented, created, it shows up as a red flash. So a lot of the tools are starting up at the origin. Some start up kind of on the research axis. And you heard a little bit, I showed you earlier, that Rapture toolkit that you could use to drag and drop the controls. As soon as we released that, people started creating tools like crazy. It became a whole lot easier to put tools up on the hub. And you can see the tools really taking off. You also see most of the tools start up on the research axis, but kind of migrate their way into education. And that's really interesting because, you know, if you think about it, it makes perfect sense with the university, the fact that there's so much crossover between education and research, but the research tends to fuel a lot of the educational activities. And that's exactly what we see. At one point, the NSF asked us to classify all the tools at NanoHub and say which ones were for education and which ones for research. And we didn't know how to answer the question. We do now, because the answer, it's not a clear story, right? It's not a binary education or research. There's a lot of duality and a lot of evolution over time. So that's interesting. All right. Now, just to kind of wind this up, I want to talk a little bit about the collaborative ways that people work together on a hub. And one of the ways that people do that is, for example, when they're working on tools. So you saw earlier, you register a tool project, you get a subversion repository, and you start working on your tool, trying to get it ready for publication. So imagine, these are all the little teams. Each one of these is a different tool project. And some projects maybe just a single developer, some have a few or three. I think typically, some have 10. You'll typically see a team size of about 3 to 5 people working on a little software tool like this on NanoHub. Now imagine for a second, every time they touch the source code and check it into Subversion, imagine you see the tool kind of wiggling around a little bit. And you'll see this in a minute. And imagine too, as they're walking through the states, you register a tool, you get a tool created, uploaded, it finally gets installed, you approve it, it gets published, and at some point you might even retire the tool. So there's this life cycle to the tool, and every time a tool changes state, in a minute you'll see a line kind of coming out from NanoHub to the tool, kind of indicating that we're working, there's a handoff there, that we're working with them to kind of help the tool change state. And the goal is to get all these tools to green. But some tools, they're bug fixes, and they go backwards, and they go all the way back to green again, and they go back and up to green again. And some tools get improved over time, and you'll see a lot of activity. So let me show you kind of a year in the life of NanoHub and all these different tool projects that are happening. I think there's about 700 projects that you'll see here. And again, each of these dots is a tool project. So each dot is a separate tool. And the goal is to get all the tools to the green state, because that means they're published. You can see them appearing around the outside rim here. You can see them shaking around as the developers are checking in code into Subversion. And every time a line comes out, there's a state change. The state change from gray to blue to green and so forth. You can see a couple of retired tools as well. You can see over the summer, there's a huge amount of activity. We typically have summer students come in, REUs and so forth, and they create all kinds of tool projects. We do some training. You can see some tools just languish. They get started, but they never finish. And others kind of go through the state multiple times. In fact, even the old tools get updated and republished over time. So this is what it looks like in terms of NanoHub interacting with the community as new tools come online and people do development. Now, the really interesting thing is inside each one of these dots, each one is a little project with like 3 or 5 developers, and there's dynamics that are happening inside there in terms of how the developers interact. So that kind of gives you the big picture, but the next thing, we drilled down a little bit. I say we, it was actually Nosh Contractor who got the idea. He wanted to see how people were interacting on NanoHub. So Nosh Contractor is a professor at Northwestern University. He got the data set from NanoHub and started studying the team dynamics in each one of those little dots. And he presented this, by the way, if you look up HubHub 2012, he gave a keynote and presented this talk on some assembly required self-organizing teams and their performance. But just to kind of paraphrase him a little bit, out of the talk, he found a few interesting things. One was that teams had more success if, for example, they had many versions. So if you improved a tool, you didn't just put it up once, but you fixed it, you improved it, you added features. The more versions you had, typically the better your ratings. It correlated with good ratings of the tool because the tool was fresh and well supported. That makes sense. He also found that if the tools were open source and if they included authors from different universities, they tended to get more citations. So if you want to get paid, if you want to do well, make your stuff open source. Make sure you have other people from different universities, hopefully all around the world. Because if you do that, you'll just tend to get more citations, period. And I guess it's interesting to think of why. It may be that these guys and their friends are all citing you, I don't know. But somehow by kind of seeding your collaborations out into the world, it tends to give you more success that way. And then along the axis of users, again, if you had authors from different countries, and again, if you had many different versions, then you would tend to get more users. So the tools with the most users had that kind of diversity. And if you put it all together, if you follow all of these strategies, you'll tend to get good ratings, more citations, and more users, which overall gives you success. Nosh has a really interesting paper. I forgot to put the reference on here, but it's called Moneyball for NanoHub or something. It's basically, the movie Moneyball, where they tried to figure out the best baseball team, not by getting the star players, but by getting what they needed on the team, right? So he has a whole paper. If you Google Moneyball and Nosh Contractor, it'll come up, and it's a really interesting read. It's exactly this kind of theory. So just to mention, I talked a lot about NanoHub, but again, NanoHub is one of about 60 hubs. So just to mention some of the other hubs that are out there, again, the one on earthquake engineering where they shake up buildings and try to see how they fall apart. There's pharmaceutical manufacturing where they're working on how to manufacture different kinds of powders and pills and capsules. Molecular diagnostics is one where they're disease agents and they're using molecular diagnostics. Environmental modeling, volcanology. There's one for cancer care. There's a new one we started recently for the NIH, for the National Cancer Institute. It's pretty small now. It hasn't quite reached some of these. It's just started. So anyway, lots of different hubs, lots of different kinds of communities. Everything, HabRE is human-animal relationships like seeing eye dogs. There are some that involve education. This one's data management. So really spans the gamut of different science contexts. And that's it. That's the nickel tour of HubZero. I hope it gave you some ideas about what it is and how people are using it. If you're interested, there are lots of hubs out there to study. I think there's a ton of data that nobody is looking at. It's kind of sad that we do all of this and generate all this data, and it's not really being analyzed very well just by a few people like Nosh Contractor. And so opportunities to jump in, and if you're trying to create this kind of infrastructure, again, the software is free, open source. You can download it, set it up on your own servers. We even have an Amazon Web Services image that you can use to start up a hub too. So I'm happy to take any questions. There's not a data science or a network science hub. I was always hoping that we'd get you guys to be the first, but maybe yet to be determined. So there's a wide open area there. Yeah?
You provided using the software with the concern stored and comments and that stuff.
Yeah, the question is about the hosting. So we actually do all of that. So we provide, for example, the software stack, and some people take it and set up a hub at their local institution, Washington State University, University of Illinois, whatever. Some people do that. Some people say, look, I don't want to mess with it. You guys host it for me. So we also offer hosting services. We got about 25 hubs that we host at Purdue for lots of different people, for SUNY Buffalo, for NIH, EPA, all kinds of different agencies, and of course Purdue. And then we also have a HubZero Foundation set up. So for people that are running the open source software and that need a little bit of help, they can buy into this HubZero Foundation, and it gives them tech support. It's only $5K to join, and it gives you like 20 hours of instant online chat kind of tech support that you can access. And you can pay as you go if you need more support and all of that. So there's a variety of things. There's a few companies out there too. There's No Innovation, a company called In3 Applications, and also BioTeam that all provide HubZero either hosting or consulting services for different organizations. So for me, the more people using it, the better. And I'm happy to have all these other companies kind of pick it up and use it.
How long does it typically take them to start up an instance? Like for an analysis, you need to see what the adoption rate was.
Yeah. Yeah, it's a really great question because, one reason, too, we call it a hub instead of a website is that you have to build a community. It's not just about putting the website up because the website goes up in 5 minutes if you use the Amazon instance. But then you got to get data uploaded. You got to fill it with content. You got to keep filling it with content. You got to feed the machine, and then the users come. A typical kind of thing is that at the end of a year, you probably have 1,000 users. And then from there on, it should double every 12 to 18 months. So it typically doubles, and it's like a Moore's Law kind of thing where it's 12 to 18. The Nice hub actually grew faster than that, so they beat those numbers and doubled faster and grew faster in their first year. But a very typical pattern is after a year to have 1,000 and then just double after that if you're doing everything right. If you're not doubling, you're doing something wrong. You're either not putting up content, it's not well advertised, the site's down, something's wrong if it's not doubling. Yeah.
As far as tool development, do you feel like you evolved with technologies, web technologies like HTML5 and JavaScript?
Yeah, great question, because we've been doing this for like 12 years now or something, so there's a lot of history in the package. But for example, what we have on the back end right now is OpenVZ containers. That's the reason we can let people upload their code, because we don't trust their code. We run it in secure containers that wall them off from everything else. So we've got OpenVZ containers running in the back end. We're running the latest VNC, Tiger VNC, and we used to have a Java connector for the remote desktop, but we actually have a JavaScript one now. So we can support, if you go to hubzero.org today, it's installed there, and you can actually run the tools on your iPad or your iPhone, and we're gradually rolling it out to all of our hosted hubs and making it part of the package as we're testing right now. So yeah, with HTML5 for the client, we have that. Of course, for the web technology, I think we do a super job keeping up there. On the back end, we're kind of looking at Docker right now, because Docker might be a replacement for OpenVZ, but so far haven't gone there. We're also looking, we've got a Moonshot rack from HP. HP has a Moonshot chassis where you can get lots of different computers, and the neat thing there is that you can buy small, cheap CPUs with graphics. So you can basically give lots of users their own graphics card. Because if you're doing high-powered visualization, you kind of need a way to inexpensively give everybody their graphics card. So we're actually investigating the Moonshot thing right now. And a lot of the work we do, too, in terms of security, trying to keep the site, all these sites secure, because we have 2 running HIPAA now, and we're doing FISMA for NIH, and there's a big security focus to make sure everything's running. So yeah, a lot of stuff happening all the time. The one good thing I like about this project is that whenever we make an improvement, it actually benefits all the hubs. When I started at Purdue, there were all these groups that were all doing their own thing, and there was no common thread tying them all together. But with HubZero, we actually have lots of, it's not just me. I have colleagues at RCAC that write proposals that build on HubZero that I think is terrific, because that gives us a stronger core that everybody benefits from. So. Yeah. Sure, thank you. Thanks for having me.